In the context of a computer, representable numbers are the elements of the number system that it's using. In other words, those numbers that the computer is capable of storing, retrieving, and doing mathematical operations on. The results of these mathematical operations eventually need to be stored, so the results of the operations must themselves be representable numbers. For a single numerical calculation, it makes sense to insist that the circuitry in the CPU of the computer must interpret the representations correctly, produce a result in the same representation, and the quality of the result, well, the result should be the representable number that is closest to the true answer. The true answer often isn't representable, and we'll see examples of that as we move through the unit. So this is certainly a reasonable expectation of the behavior of a computer in the context of arithmetic calculations and finite number systems. Even with the restriction that the result of a single mathematical operation should be the representable number closest to the true answer, finiteness can cause some unusual results to occur. Let's think about this using the 3-digit floating point example that we've been working on. Let's pretend this is MATLAB system, so I can type MATLAB commands. Assign J 30.9. That's fine because 30.9 is representable. Assign F 2030. That's fine because that's representable. Compare J to J plus 1. Well, there's a calculation on the right-hand side, J plus 1. The exact answer is 31.9, and 31.9 is representable. So J plus 1 must lead to 31.9. 31.9 is not the same as 30.9, so that expression involving a relational operator evaluates to false. What about F = F plus 1? Let's think about the right-hand side, F plus 1. The exact answer of F plus 1 is 2031. 2031 is not representable. The closest representable number to 2031 is 2030, which is F again. Therefore, this expression built of a relational operator will evaluate to true. However, if we evaluate 1 = 0, that clearly will be false. So, depending on values, F = F plus G can be true, while G = 0 is false. Normally, for arithmetic, the cancellation rule holds. If F = F plus G, then I can add negative F to both sides, and clearly G will equal 0. But in this case, the cancellation rule doesn't always hold, and that's predominantly due to the finiteness of the number system. Let's talk a little bit more about expectations. First, let's consider real numbers, the idealization that we're always working in. There's arithmetic operations on real numbers, and they always result in a real number. We notate them as usual. Now, sometimes we might need a little more clarity, and I'll use the command exact to indicate the exact sum of x, y, or the exact quotient of f and g, and so on. By contrast, in the computer, we're always dealing with representable numbers and machine arithmetic. Computers can store representable numbers and compute on representable numbers, and the results of those computations have to be representable. Let's let R of x denote the representable number closest to the real number x. Let's let op denote the machine arithmetic. Here, op plus xy denotes the representable result of adding two representable numbers, x and y. Based on our expectation, we really want this to satisfy that the representable result should be the closest representable number to the exact answer. That's exactly what I have written there. So this is a requirement we, the users of the computer hardware, place on the computer hardware manufacturers, specifically the arithmetic processing unit in the CPU. Even with that restriction, that single operations always produce the closest representable number to the exact answer, there are issues that can arise. We already saw one when adding 1 to a number didn't change its value. Let's look at a different manifestation of this. For real numbers, addition is always associative. For any real numbers, x, y, and z, it's always true that you can first add x to y and then add that result to z, or instead you can add y to z and then add that result to x. It's always an equality. It's always an equality. It's not necessarily true in fixed precision and finite number systems. For representable numbers x, y, and z, it may be that, and then I have this complicated expression here. Let's parse out what it means. On the left, the innermost operation, which happens first, is that x is added to y using the finite number system, resulting in a representable number, and then z is added to that, resulting in a representable number. On the right-hand side, first y is added to z, resulting in a representable number, and then x is added to that. It may be that these are unequal, unlike the result for real numbers, where associativity always holds. What can occur that would make that happen? It might be that the rounding to representable is different depending on the grouping. One grouping results in round downs, the other round ups, and at the end the result is different. Let's take an example with three representable numbers in our three-digit system, 11.2, 3.74, and 1.2. Certainly as real numbers, these are equal. Associativity holds. Let's trace through the steps in the machine version of these, where the operations are done in the finite number system. Start on the left. The innermost operation computes the exact result as 14.94, but that's a four-digit number and our number system only allows 3, so it's rounded down to 14.9. Then the next operation occurs, adding 14.9 to 1.24. The exact result is 16.14, which is rounded down to yield the final result, 16.1. How about the other side? The first operation results in the exact value of 4.98, which is representable. No rounding occurs. The next step adds that to 11.2, resulting in the exact value of 16.18, and the rounding to nearest representable gives 16.2. These are not equal. What's the exact number? The exact number is 16.18. On the left, the final result did not end up with the closest representable number to the exact answer. What we see is that even though each single operation always produces the closest representable, two successive operations do not necessarily have that guarantee. Dealing with the effects of round-off on the behavior of computational algorithms is a focus of numerical analysts. Since normal equivalences of arithmetic don't apply, for instance, cancellation rule, associativity of addition, those are two examples we've seen, as well as associativity of multiplication and distributivity of addition and multiplication, two different but correct implementations of the same algorithm may give different results when applied to data. Understanding how such errors can propagate and maybe grow, and how to recast the algorithm to be less affected by these issues is a critical aspect of scientific computations.